Hello everyone, welcome to this introductory tutorial on using Atomic Model Builder, the tool for creating custom atomic models for use by the Prism Computational Sciences codes. PrismSpect, Propaceous, Spec3D, and HelioCR are Prism's plasma simulation codes which may utilize atomic data when performing detailed atomic energy level structure calculations to ultimately calculate opacities and other plasma properties. The atomic model is your way of controlling which atomic levels are included in a calculation. Full atomic datasets are distributed with Prism codes for elements up through krypton, both in the form of Prism's own AT base format, as well as FAC, the flexible atomic code. FAC is freely available on GitHub, so you can even create your own atomic dataset. Atomic Model Builder accesses either an AT base or FAC dataset and allows you to select from the levels available in that dataset. While in principle, one could include all levels in a simulation, this will typically result in impractically long runtimes or too much memory consumption. Selecting only those transitions which are relevant to your simulation can make an immense difference to the performance of the calculation. Let's start from the perspective of PrismSpect in an argon-doped deuterium implosion example similar to the one from the PrismSpect introductory video. Here, we can see the different default atomic models which are available for use. While these models may be sufficient for some cases, they are really designed to be a starting point for simulations where more careful consideration of relevant atomic levels may be important. When we did this example, we used the default emission K-shell spectroscopy atomic model. However, this model actually isn't detailed enough to see typically observed spectral features in this regime. There are several lithium-like satellites which appear at these plasma conditions, but as we will see, they will be missing from the spectral results. Let's use the View button to open this atomic model file with Atomic Model Builder. If you are using Linux or Mac and the button does not work, you may need to set the path to Atomic Model Builder in Preferences. Atomic Model Builder can also be launched on its own. The file pointed here contains the full atomic data for this element. In this case, we are using the AT-base atomic data. You can see options for opening FAC data in the file menu. Again, both AT-base and FAC atomic data are distributed with Prism codes. The atomic model that we work on in this interface allows for the selection of subsets of that full atomic data. The model we opened is a emission K-shell, which means we will have argon in highly ionized conditions. This is why there are 0 atomic levels selected for these lower ionization stages. Double-clicking an ion, we can see all the possible atomic levels for that ion on the right. We can look at argon 15, where we have only the ground state selected. The energy of each level given in this column is relative to the ground state of this ion. So, a ground state will always have 0 for its energy. We can add another column for each level's statistical weight by toggling that in the Show menu. Two more options will be available starting with version 4.3.0 for showing the level index used by Prism codes and show displaying the number of electrons over here instead of beryllium, like, and so forth. Having only the ground state selected for argon 15 allows this state to act as a sink for populations in the event that the plasma is colder than expected. For argon 16 through 18, we have more levels selected to allow for transitions in these ions to be included in the calculation. Looking at argon 16, and scrolling down in the right, you can see that some levels are selected for this ion and some are not. As we mentioned, this default model may not be sufficiently detailed for your purposes. We will run PrismSpect with argon in conditions where we need to include more atomic levels in order to observe lithium-like satellites associated with the helium beta emission line. First, let's run PrismSpect with the default model. Here, we're loosely mimicking the condition in inertial confinement fusion experiment in the early stages of the implosion, where temperature and density are still relatively low and the size is relatively large. We'll give it a planar geometry to preserve some of the opacity effect in the helium beta line, and we will specify electron density. We will run the single temperature density point of 500 eV, 10 to the 23rd electrons per cubic centimeter, and a thickness of 200 microns. Let's assume LTE populations for the atomic levels. And the photon energy range of 3500 to 3800 eV will show us the region around the helium beta line. Let's run this. Looking at the emission spectrum, we can see just the helium beta line standing alone. However, we might know that other emission features should be present in the spectrum, namely the lithium-like satellites around this helium beta line. These come from the relaxation of one electron from a doubly excited state in lithium-like ions, where the other excited electron, referred to as a spectator electron, is causing the screening effects on the transition, giving them a red shift. Let's add these atomic levels by customizing our atomic model. Let's begin from the starting point of the default emission K-shell model. When you alter this, make sure you use Save As rather than overwriting the default model. It's possible that your version of Atomic Model Builder will protect you from doing this. Let's use Save As to save this custom model somewhere. We want to add the levels needed for these satellite transitions in the lithium-like ion. Double-clicking on this ion, we can see all of its available levels. Scrolling down, we can see that these singly excited levels are included up through n equals 6, and then we reach a group of doubly excited states where the highest level is n equals 2. These will allow for satellite transitions around the helium alpha emission line, where the electron is decaying out of the n equals 2 level. Below these, we can see doubly excited states where the highest level is n equals 3. If we included these, it would allow for the helium beta satellites we are hoping to see. Rather than selecting these levels individually, let's look at some of the more powerful options which are available when you right-click on an ion on the left. Here, we can do large-scale operations for this ion, or on multiple ions at once. Here, we'll just apply this to the lithium-like ion. We can do things like select only the ground state, deselect or select all levels, or deselect states with principal quantum number greater than a certain number. In addition to singly excited states, atomic data contains multiply excited or auto-ionizing states, which can be controlled with these other options. Hollow atom states are only available in FAC data, and LBIT are implicit or grouped levels, which are only available in AT-based data. For our purposes, let's start by selecting all states for the lithium-like ion, and then choose this last option to deselect states with n, or principal quantum number greater than 6. We do this because, at the density we are using, we do not expect those high excitation levels to exist in the plasma. We will discuss level collapsing more at the end of the video, but now we will also make sure we set the level of detail to fine structure for the new levels we added. We can go to Set Collapse Model. This allows us to collapse or expand groups of levels. If we click on our lithium-like argon-16, we can view the level of detail for the states on the right. In the middle, we can control the level of description for groups of levels, or super configurations. The states we added were doubly excited states, where one of the K-shell electrons was promoted, leaving one left in the K-shell. So let's select all of those super configurations. Then, we can click Edit Parameters to control the collapse model for just those super configurations. Let's scroll down in order to see the effect this will have on some of our double excited states. When we click Find Structure and click Apply, we can see the expansion of detail here for those super configurations. Click OK. One more thing, see that we are controlling the collapse mode for the populations part of the calculation. We want this also be applied to the spectral calculation in order to see these new lines in detail in our resulting spectrum. If we click Apply to Spectra, we can apply this collapsing to the spectral part of the calculation as well. In fact, for a simulation using LTE populations, the populations collapsing is ignored, so here we are really only concerned with the spectral collapsing. Simply closing this window with the Close button will preserve these changes. Now we have added these lithium-like satellite transitions to our model in fine structure detail. Going back to Prism Spect, let's click Custom and browse for our atomic model file. Let's run Prism Spect again. Now in the spectrum, we can see more structure than just a helium beta line. If we click on Spectral Components, we can select our lithium-like ion to separate out the part of the spectrum which comes from that ion. We can see that these red emission lines are coming from this ion. This example demonstrates the importance of understanding the atomic physics in your simulation and how you can use Atomic Model Builder to include the necessary transitions while remaining practical by omitting atomic levels which are not relevant. Let's work a little more with the concept of model collapsing. Some situations may require a level of description all the way to fine structure. However, it may be the case that that level of detail may not be necessary. If you cannot resolve atomic levels at that level of detail, either due to the physical coupling of states at those plasma conditions, or simply due to the resolution of your detector, you can save a lot of computation time by grouping or collapsing the levels together. It is important to have a good understanding of your physical system in making these decisions of accuracy versus calculation speed. Let's go back into Set Collapse Model and again click on our lithium-like ion. Let's select these particular doubly excited states again and edit their parameters. Previously, we applied Find Structure by clicking here and clicking Apply. Term Split is a level of collapsing which is available for AT base only. Leaving these both unchecked will result in collapsing the model to configuration average. We could even collapse fully to super configuration level by clicking this Collapse All button. But let's simply leave these two boxes unchecked in order to apply configuration average collapsing. Let's get the first helium beta satellite state visible in the tree. Hitting Apply, we can see our desired states become collapsed to their configuration average level of detail, and we can see that this was not applied to levels which were not selected. We can also specify this only for a specific n level, and we can even apply this to all levels of this ion, or even to all levels of all ions in this element if we click either of these buttons. Let's continue just applying this to our helium beta satellites. Another way of applying collapsing criteria to all levels in this element is with the drop-down menu in the lower left. You can also import a collapsing model which was previously exported from the File menu. It's important to note that changing the level of tree collapsing on the right will not actually apply to the model collapsing. This will not affect the collapse model. This tree is for information purposes only. Remember to apply this to spectra as well. Let's save this collapsed model as another custom model. Let's load that into Prism Spect and run again. Let's look at the spectrum and again separate out the argon-16 component. We still see lithium-like satellites, but now with less resolution due to the collapsing of levels in the atomic model. If you are using a platform that lets you open multiple instances of Prism Spect, you can open a second results window in order to drag one plot onto the other. In summary, exercising your knowledge of the atomic physics in your system, you can make decisions about which atomic levels are important to include, and what amount of atomic level collapsing you can use to greatly reduce your calculation time and memory consumption without sacrificing important physics. Note that this particular example ran quickly due to its simplicity. However, you will likely be using Prism codes for much more complex systems where proper use of Atomic Model Builder can make vital improvements. More details about level collapsing and other aspects of Atomic Model Builder can be found in the documentation of Prism codes. For example, within the Prism Spec documentation, the appendix document here. This concludes this tutorial for the use of Atomic Model Builder for Prism codes. Thank you for watching.